Hi, folks. We've been talking about motion in one direction so far in the class. Uh, we've primarily been focused on horizontal motion, so motion in the x direction. We can certainly also have motion in the y direction, just straight up and down. If that's the case, we change our kinematic equations. Everywhere that before we saw an x, we've replaced that with a y instead. So now our displacement is just y instead of x. But other than that, those equations are really the same. Now let's take a look and see and talk about the primary type of motion we're going to be concerned about in the y direction. Well, when I think about motion in the y direction, I think like of something like maybe a ball getting thrown up in the air, or something where gravity is the only force that's acting on it. So if that's the case, if I throw a ball up in the air, once that ball leaves my hand's no longer working on it. It's just going to be acceleration that's pulling it, or it's just going to be gravity that's pulling it back down towards Earth. The size of the acceleration due to gravity is 9.8 meters per second squared. That acceleration always points downwards, so we would say that the acceleration has the acceleration is a vector, and since it points downwards, that acceleration is negative 9.8 meters per second squared. Now, anytime I've got an object up in the air where the only thing that's acting on it's gravity, that object is said to be in free fall. That it doesn't matter whether the ball is rising, or the ball is at its apex, or the ball is falling back down. Any part of that motion, we call that motion free fall motion. This, of course, neglects air resistance, which is primarily what we're going to do in this class. It's reasonable to neglect air resistance as long as maybe things don't get moving too fast in terms of our day-to-day macroscopic objects that we deal with. So let's take a quick look at an example, the throwing the ball up. We'll make upwards the positive direction, downwards the negative direction. There I've got a ball rising, reaching its apex, and then falling back down to where it started from. And I can think about the acceleration. So as the ball is rising, let's see, gravity is working against it. And so what we see there is that we've got a velocity vector that's upwards, an acceleration vector that's downwards. And so as a result, those velocity vectors there are getting smaller and smaller as we work up. So we see the bottom one looks fairly large, and then as we go up, we get smaller and smaller and smaller. All right, so the ball is slowing down. At the apex there, the ball, just for the briefest moment in time, reaches zero velocity. So that's a turnaround point. We go from having a positive velocity as it's going upwards to having a negative velocity, a downwards velocity, as it's falling downwards. It's got to cross the 0 point somewhere. So that 0 point for velocity is right at the top. Anytime something's at the peak of its motion, its velocity in the y direction is 0. Okay. Gravity hasn't turned off. Gravity's still there. Gravity is what's causing this ball to change direction. Gravity still points downwards at the top. And then as we work our way back down, we can see that those velocity vectors are getting longer and longer and longer. This makes sense. Acceleration is working in the same direction as velocity, so we would expect the ball to speed up as it approaches the ground again. Sorry that my head's in the way here. It says the ball's acceleration is negative 9.8 meters per second squared at every instant of the motion. So from the moment the ball leaves my hand until the moment the ball smacks back into my hand, the acceleration of the ball is negative 9.8 meters per second squared. That's what it is on the way up. That's what it is at the turnaround point. That's what it is on the way back down. The acceleration is always negative 9.8 meters per second squared. All right. So I have a question for you guys. I want you to read the question and then pause the video and think about it for a moment. And then go ahead and pick your answer. unpause the video and see if your answer agrees with the correct result. All right, so pause now. All right, so we were curious about the acceleration of the ball at the peak of its flight. So right there at the apex of its flight, the acceleration of the ball is still negative 9.8 meters per second squared. Gravity is still pulling downwards on that ball. So it's going to have an acceleration. Acceleration does not turn off, and that acceleration is negative 9.8 meters per second squared. All right, so I've got a question for you guys. This is the Center for the Sciences at Radford. It says we've got a kid that's climbed to the top of the Center of the Sciences, and that kid is going to drop a rock from a height of 30 meters off the ground. And I'm curious about the velocity of the rock just before it hits the ground. This is a little weird. So I ask about the velocity of the rock just before it hits the ground, and then I ask how fast is the rock moving at that moment. Now that's kind of confusing because in our everyday language, it seems like I would be just repeating the exact same question. So it's asking about its velocity and then asking about how fast it's moving. Let's see what the result ends up being. All right. Okay. So I'm going to do my best to draw a sketch here. Real crude sketch. Unfortunately, I'm drawing with my finger. Oh, I'm drawing in red. I forgot. There we go. Turn that back on. There we go. There's the Center for the Sciences. Drawings not to scale. But Jimmy is a giant, if so. Okay, so there's a height of 30 meters, and Jimmy's dropping a rock there, and then the rock is falling down there. Let's see, something like that. That's a fair sketch. All right. So let's talk about something here real quick. I ask about the velocity of the rock when it hits the ground, or just before it hits the ground, or I could say when it hits the ground. The velocity of the rock when it hits the ground is not 0 meters per second. So if I ask a question like that, what's the velocity of the rock when it hits the ground? I'm not interested in the velocity of the rock after it comes to a stop. I want to know right at the moment of impact, what's the speed of that rock? What's the direction that it's moving in? Now, for instance, let's say that, unfortunate accident happens. Let's see, you have a friend, everything ends up being okay. But you have a friend that maybe loses control of their car on the ice and hits a tree. And of course, the first thing you're going to ask is, are you okay? And they'll say, yeah, I'm okay. The car is just kind of a mess. And then the next question you would ask is, well, how fast were you going when you hit the tree? And that person wouldn't say, well, I was going 0 when I hit the tree. No, they would talk about maybe, I think I was going about 20 miles per hour when I hit the tree. Now, I'm telling you this story because I'm trying to draw a connection for you. The velocity of the rock when it hits the ground is not 0. It's however fast it was moving just right at that instant. Maybe you could think about it as if it being right before impact. In the same way that your question about how fast the car is going, you really don't care about the fact, you care a little bit about the fact that the car came to a stop. But what you're really asking in that instance is, how fast was the car moving right before it hit the tree? All right. Anyway, back to our problem here. We've drawn a sketch. Our next part in this process, or our next step in this process, is to think about our table of values. Okay, so we've got displacement, initial velocity, final velocity, acceleration, and time. The displacement here, the ball drops 30 meters. It drops 30 meters. That means that our displacement is negative 30 meters because its final position was lower than its initial position. Its displacement is negative 30 meters. Let's see, the problem says that Jimmy drops the rock. All right, so if I drop something out of my hand, its initial velocity is 0. So that's 0 meters per second there. Final velocity, we don't know that. Acceleration, we know that this is negative 9.8 meters per second squared. And lastly, we don't know the time for the rock to drop. So I apologize for the crudeness there. Like I said, I'm drawing with my finger. Maybe I'll try to do better on the next one. But there's our problem, or there's our table of values. Displacement is negative 30. Initial velocity is 0. Final velocity we don't know. Acceleration is negative 9.8 meters per second squared. Time we don't know. And the thing that we're really concerned about in this problem is how fast is that ball moving at the moment of impact? What's its velocity at the moment of impact? All right. So I'm going to give us a new slide to work with. Okay, so if we think about our kinematic equations, we can maybe pick out one of those that is going to work out for us given the information that we have. And that equation maybe looks like this. Okay. So our final velocity squared is equal to our initial velocity squared plus 2 times acceleration times displacement. Let's fill in our values that we have. I'm going to drop the units because of the difficulty I'm having with just drawing in general. So I'm going to leave the units off here. Normally I wouldn't do that, but I'm having enough problems, enough trouble as it is, without giving myself extra things to put in. Okay. All right, this gives us a final velocity squared of, let's see here, a negative times a negative is a positive. This is 588. If we take the square root of that, we'll end up with 24.2 meters per second. But here's where we have to be really careful. When we take a square root, we have to keep in mind that a square root can have both positive and negative values. You can think about it like this. The square root of 9 is 3. The square root of 9 is also negative 3 because negative 3 times negative 3 equals 9. So when we end up with an equation that looks like this, where we've got v squared is equal to some number, we have to think about, do I want the positive or negative root? In this case, at the moment of impact, the ball is moving in the negative direction. So we would want to make sure that we include that negative sign there. That's something that we have to remember to do. So the ball's final velocity is negative 24.2 meters per second. Now, that was the first question I asked. The second question I asked was, how fast is the ball moving? So that question asks about the size of velocity. If I ask how fast is the ball moving, I'm asking about its speed. Its speed is just the size of velocity. Its speed is 24.2 meters per second. There we are.